In combinatorial optimization, the longest path problem, or LPP, asks for the longest simple path in a given graph without revisiting any nodes. It is a canonical NP-hard task. If you need to find the shortest path between 2 points, standard methods like Dijkstra's algorithm can calculate it in polynomial time. To find the longest path, however, there are no shortcuts. The solver must exhaustively enumerate the possibilities. As you add nodes to a graph, the size of that search space scales at O of n factorial. The computational requirements escalate with every single addition. This chart tracks the O of n factorial growth in possible permutations as we increase the node count, plotted against a threshold of 10 to the power of 80, the estimated number of atoms in the observable universe. By the time we reach a graph of exactly 63 nodes, the search space reaches 1.9 times 10 to the 87th power permutations. This exceeds the estimated atom count of the entire universe by 7 orders of magnitude. Traditional deterministic algorithms evaluate these paths one by one, step by step, in sequence. Evaluating that many states using brute force computational power is a physical impossibility. Solving dense graphs at n equals 63 requires a total departure from standard enumeration. The current industry standard for tackling these tasks is blind depth-first search. On dense bipartite graphs, where nodes are highly interconnected, this method hits a wall quickly. This bar chart illustrates that exact failure point. At 19 nodes, the standard solver successfully resolves all instances. Add 1 node, and the success rate drops to 70%. At exactly 22 nodes, the algorithm completely collapses, yielding a 0% success rate. In 2026, independent researcher Andrés Sebastián Pirolo published a generic low-level architecture that bypasses this wall. It resolved the 10 to the 87th search space of an n equals 63 graph in exactly 0.116 seconds. A consumer-grade 8-core mobile processor achieved this 0.116-second resolution, producing in milliseconds what normally overwhelms industrial server farms. This performance is the result of a 3-tier symbiosis: mathematical structural pruning, register-level silicon execution, and genuine thermodynamic physics. The first step to breaking O of n factorial is eliminating the vast majority of the search tree before the computer explores it. Pirolo achieves this through the heuristic of prime factors, or HFP. The algorithm classifies every node in a graph based entirely on its number of distinct prime factors. Integers with exactly 2 distinct prime factors are sorted into a shell category, while all other integers are classified as core. This classification isolates what the paper terms the HFP anomaly. Empirical data proves that optimal solution paths overwhelmingly favor core nodes, comprising roughly 88.9% of the path, whereas random routes average only about 40%. The solver exploits this anomaly by applying an 80-20 exploration rule. At every decision point, it probabilistically forces the search toward a core neighbor 80% of the time, keeping the search concentrated on structurally favorable nodes. As the path builds, the algorithm constantly checks the ratio of core to shell nodes. If this recipe falls below a specific beta threshold, the solver instantly aborts the branch and backtracks. This threshold calculation is executed using pure integer arithmetic. Floating point division is entirely removed from the critical path to maintain maximum processing speed. By isolating the prime factor structure of the graph, this heuristic eliminates 97% of the dead-end search space before the processor evaluates a single full path. Even with a 97% reduction, the remaining 3% of the permutations still overwhelm a standard CPU. The bottleneck is no longer the math, it is memory latency. Standard algorithms stall because they must constantly fetch data from RAM, L3, and L2 caches. Every cache miss or heap allocation wastes hundreds of clock cycles, where the processor does nothing but wait. Pirolo's architecture maps the entire problem state, the adjacency map, the visited mask, and the node classifications, directly into 64-bit CPU registers. To move to the next valid node, the algorithm uses a single chain of pure bitwise operations, AND, NOT, and XOR, combined with dedicated hardware instructions like count trailing zeros. This entire transition sequence executes in exactly 4 CPU clock cycles. There are 0 memory access stalls and 0 branch mispredictions. By abandoning the traditional memory hierarchy, the CPU stops acting as a data manager and operates as a pure logic engine, evaluating millions of structural states directly inside the L1 cache. Aggressive pruning creates a vulnerability. Deterministic algorithms that prioritize specific nodes inevitably get trapped in cyclic attractors or dead-end subgraphs made entirely of core nodes. Escaping these traps requires injecting randomness to force the algorithm down alternate paths. However, traditional software pseudo-random number generators require complex mathematical transformations that burn precious CPU cycles. The architecture solves this with a chaos engine. It initiates deliberate, lock-free race conditions. Two concurrent CPU threads continuously write to the exact same volatile memory address without synchronization. The winner of this race condition is decided by Johnson-Nyquist noise. At any temperature above absolute zero, the charge carriers in the silicon lattice undergo inherent thermal agitation, introducing picosecond-scale timing uncertainties into transistor switching. The outcome is further randomized by micro-delays in the cache coherence protocol arbitration, caused by physical crosstalk and electrical noise within the chip itself. By intentionally triggering undeclared behavior, the architecture harvests thermodynamic entropy directly from the physical silicon. This generates true stochastic navigation at zero computational cost, providing the exact randomness needed to escape mathematical traps. The solver succeeds through a specific division of labor. Structural pruning eliminates the dead ends, bitwise logic provides the register-level speed, and physical entropy breaks the local minima traps. Because the entropy enables probabilistic tunneling, the solve times do not scale linearly with the problem size. In testing, a 50-node graph was resolved in just 3 milliseconds, natively discovering structurally favorable paths faster than smaller, less complex graphs. This scatterplot maps performance from n equals 50 to the 64-bit limit at n equals 63. Despite astronomical permutation growth, every instance was solved cleanly beneath the 100 millisecond threshold. The final n equals 63 benchmark, representing 10 to the 87th permutations, was self-verified on a mobile chip in 0.116 seconds. To verify the resilience of this physical randomness, the system was subjected to a thermodynamic stress test. The CPU was intentionally saturated with concurrent floating point operations to induce maximum thermal throttling. Under these degraded conditions, the clock frequencies dropped, slowing the absolute time, but the algorithm produced bit-perfect results with zero errors. The logic is thermodynamically invariant. The n equals 63 barrier fell when the architecture abandoned deterministic software constraints, allowing the raw physical chaos of the hardware to compute the solution. Beyond theoretical graph mathematics, longest path optimization is a severe bottleneck in industrial engineering, particularly in VLSI electronic design automation. Tasking algorithms with critical path analysis or pin-to-net routing on dense circuit boards currently consumes massive server farms and limits hardware development cycles. Because Pirolo's pipeline operates entirely on pure bitwise logic and/or XOR, it can be mapped directly into Verilog or VHDL. This opens a clear path for massively parallel FPGA or ASIC acceleration directly on the silicon. This architecture is a functioning proof of concept for thermodynamic computing. It points to a framework where the volatile physics of the silicon lattice are no longer suppressed, but harnessed as the algorithm itself.